Hi, in this video we're going to be talking about Chapter 12, Section 1, which is about three-dimensional coordinates, specifically rectangular coordinates. So the general idea is that since we live in a 3D space, one of the things we most want out of a calculus, out of a mathematics, is to extend, so this is our idea, we want to extend our ideas of rectangular coordinates the XY plane, our XY system, into a third dimension. And this will be done using a z-axis. We'll use a z-axis to do this. There are two ways of drawing a z-axis coordinate system. There are actually lots of ways of drawing it. I guess I'll get more into it. But for this class, there are two ways I like to use. Option one is sort of a top-down perspective, where we'll make an X, and then through the center of that X, through the vertex maybe is what you would call that, we're going to make another axis. So what this is doing is we have an x-axis and a y-axis and a z-axis. And what this is doing is it's sort of saying like a top-down view. It's sort of like we're over and above looking down at an angle at the XYZ space. Or we might use something where we start off more rectangular, like our normal XY plane, and then we're picturing another axis going into and out from the page, or the screen in this case. And that would still have to be X, Y, and Z. Just to be clear, we're talking about the positive X and the positive Y. Over here would be the negative Y. Over here would be the negative X. Sorry, this is the positive Z. This would be the negative Z. And just to be clear here, that would be the negative X, that would be the negative Y, that would be the negative Z. We're usually not going to bother labeling those every single time. We're going to just have the letter on the positive side of the axis. Whichever system we use, whether we're looking at it from the front on the right, that's sort of a front view and we're picturing in or out, or from the top-down view, we want to make sure in our system that we follow the right-hand rule. And this will actually come into play over and over and again in this class. So we're going to follow the right-hand rule, which is if you picture a right hand, this would be the z-axis, so it's a right hand, be careful. I'll say why in a second. This, if you point your fingers along the x-axis, along the positive x-axis, and your thumbs pointing along the positive z-axis, what's happening is your y-axis is coming out of your palm of your hand. This is the palm of your hand. That's why it has to be the right hand. I can't draw well enough to draw an actual right hand where you could actually notice that it's supposed to be the palm. But that's the idea. If you take your right hand and you point your fingers along the direction of the x-axis, your palm along the direction of the y-axis, then the z-axis has to stick up from here. That's the convention we use. Left-handed systems are possible, but I've never seen them in the American education system. So, here we go. So let's do an example. We're going to try to graph the point 2, 3, 4. Basic point. In this system, our coordinates are x, y, z. Still in alphabetical order, the x and the y still come first. So if I wanted to graph, I'd have my x-axis my y-axis, and my z-axis, coming right down the center of that x. And we're going to just try to graph 2 along the x, 3 along the y, and 4 along the z-axis. And just to be clear again, that's the positive x, that's the positive y, that's the positive z. We're going to draw a sketch line coming out of the x equals 2, running parallel to y. We're going to draw a sketch line coming out of y equals 3, running parallel to the x. And this intersection of those two lines is the projection of our point. That's 2, 3, 0. And this is lying in the xy plane. The xy plane, the plane you've done all your math in up until now, that's sort of the three-dimensional idea you're supposed to be looking at, is something in the xy plane is kind of going down because we're looking at it from above. And now, starting from that projected point, we're going to lift it out in the direction we want in the z. So I'm going to go from this point, and I'm going to try to trace a sketch line up along the z-axis. And I'm also going to connect that dot back to the origin. So this gives me an idea of how much this kind of a fall, the second line I drew, this fall is showing me where 0 looks. So I want to copy it down, but starting from 4 to see where I should land on the projected image. So I'm just going to try to copy that slope down. And right here is the point I would find. And we're kind of thinking of this resting in 3D space. So that should give you some sort of visual of what we're doing. We are lifting these points out of the plane. All right, so what I want to talk about now is that with 3 axes, three coordinate axes, we now have 8 distinct regions or octants of space. So again, just like we would talk about the XY plane, now we're going to talk about the 3D space. So sometimes people say 3 space or just 3D space. I'll probably alternate. We don't have numbering system for all of the octants like we might. There's efforts been to generalize them, but I just want to note that the first octant is clear. The first octant, the definition here would be the region where x, y, and z are all greater than 0. Where everybody's positive. Everyone agrees that that's what the first octant would be. All the other octants are other places in space. Other places in space. Okay, so now we have a basic idea, kind of what things look. Let's go on to the next example. There's 3 important planes you need to know and need to be able to find. I'm going to use 3 different colors here. Each time I'm going to be drawing on my X, Y, Z plane. Sorry, my X, Y, Z axes system. In this system, we'll draw the XY plane in blue. So what we're talking about here, and it's hard to draw this by hand, So watch for the GeoGebra video, but I'm going to try to show you. We're just trying to think about it's the region in space where I'm going parallel to the y-axis, parallel to the x-axis, and then parallel back to the y. It's sort of the floor. It's sort of the floor. You're used to this plane because it's where you've done all your math, but then we're coming out above and below that plane. So that's why we usually think of it as like the floor of a room. We also will have the YZ plane. So the YZ plane, using a very similar idea, and now I broke my rule, and you'll see it's hard for me to hit that exact spot where they should meet. We'll be saying that's good enough. So instead, now I'm leaving out the x-axis. If I was trying to draw the YZ plane and shade it nicely, I would go parallel to the parallel to the y-axis, touching the top of the Z, parallel to the z-axis, back parallel across the y at the bottom of the z, and then back parallel like that. And what we'd have here is kind of a screen across the YZ axis with the X axis projecting out from it toward us and then back through it away from us. And then we'll do one more, yes, in green. We'll talk about the XZ plane. Oh. Talking about the XZ plane. So, X marks the spot. The Z-axis crossing through the middle. Same trick now with the X and the Z, though. We're going to draw a line parallel to the Z-axis through the edge of the X-axis. Then we're going to draw a line parallel to the X-axis through the top of the Z. Now we're going to come back down, and now we're going to try to make a line that's parallel to all of them. Okay, that's the best we're going to do. So, again, here you're picturing the y-axis coming in and out of that rectangle. Okay, I want to talk about the equations of each of these three planes. I want to quickly talk about the equations of each of these three planes. So, the equation of the xy plane is the idea that we're having coordinates any x, any y, but the z has to be 0. That's the coordinate we are restricting here. We have no lift off the floor. So this would be the equation z has to be 0, and the other two are unrestrained. The YZ plane, so if the origin is a corner of our room, the YZ plane would be like our left wall. Again, here's what's happening. The Y can be any value we want, and the Z can be any value we want, but we're stuck. We can't go out from it or back into the screen. So the X is 0. So that would be the equation for the YZ plane. And the XZ plane is what you probably would think at this point. So we're having the Y equals 0. So in each of the planes, what you have here is a situation where you're constraining the one variable, and that's the variable that's left out of the name. So if you ever get confused and we start talking about the YZ plane, you should think, okay, that's the one without any x's. And so we'd have x equals 0. And this is going to be important. A lot of times we'll talk about the bounds of these. So I know these pictures aren't the most clear. I hope you can try to visualize it. I'll probably publish a video separately about GeoGebra to help you visualize both this and the last example. The last things I want to talk about is a distance formula. And luckily for us, a lot of these formulas will be based on the previous x and y stuff with extra dimensions. So it'll be useful to recall that in 2D, what we had was point 1 at x1, y1, and point 2, x2, y2. The distance from P1 to P2, which our book writes like this, would be based on the Pythagorean theorem. We would find the change in the x's squared plus the change in the y, the y squared. And then we would take the square root. And it's because if we have point 1 and point 2, we can just make a right triangle. So luckily for us, in 3D, this works the same way. In 3D, our points would have 3 coordinates. And you would do exactly what you think you would do. So the distance would be add another component. So still the change in the x's. In teaching this class previously, some students end up thinking there's going to be a cube that's going to show up. No. The distance formula is still based on Pythagorean theorem, so we're still not dealing with any cubes. It's all changes squared. That's the metric we're going to use in our coordinate system. So a quick example. Find the distance between P at point 2, -7, -1, 7, and Q at point 1, -3, 5. It's a pretty straightforward application of the formula. I'll give you a chance. 3, 2, 1. So the distance here, we'll use the other notation. We'll use the other notation. The distance from P to Q would be 2 minus 1. You can do it in either order. I just picked 2 minus 1 because it looked easy. But once you pick that order, you got to stick with it. Actually, you don't, because everything's getting squared. But teachers like to say that. 7 minus 5 squared, which is 1 plus 4 plus 4, which is the square root of 9, or 3. So that's the distance between them. A problem I like to ask on the homework is an application of this. So we'll talk about show A at 3, 4, 1, B at 4, 4, 6, C at 3, 1, 2, make an isosceles triangle. So the way we would do this is to recall the definition of an isosceles triangle, and to show that it's an isosceles triangle, you'd have to show 2 sides are equal in their length. So you would just start computing some lengths here, and why don't you try it out? Find the length of AB, find the length of AC, and find the length of BC. Go ahead. I dare you. Okay, so the length of AB should be on -1 squared plus 0 squared plus -5 squared, which is root 26. AC, I'm getting 0 squared plus 3 squared plus negative 1 squared, which is root 10. And BC, I'm getting 1 squared plus 3 squared plus 4 squared, which is root 26. So since those two match, so isosceles. That's all it would take. You should think about how it would work to show that the triangle is equilateral or to show the triangle is scalene. No sides are equal, right? But it would all come down to the distance formula. The next thing I'm going to show you is a midpoint formula. Midpoint formula. And this comes up, it's in one of the exercises, but I just want to go over it because, again, this is going to be useful for a few of the things we do, but not much. That's why the book can put it in the exercises. The midpoint, and we'll use the letter M, of P1 at X1, Y1, Z1, and P2, X2, Y2, Z2 is found by taking the average of each coordinate. So M would be X1 plus X2 divided by 2. It's adding, it's not the difference, it's not like the distance formula, comma, Y1 plus Y2 divided by 2, Z1 plus Z2 divided by 2. So you literally just add the coordinates up and divide. You should be able to imagine how this formula would go. So notice the output is a coordinate. It's giving you an X and a Y and a Z. Whereas the distance, the output is a number. So I'm going to end this video here. The next video, part 2, will cover spheres and other applications of these two formulas. So thanks for watching this one, and I'll see you in the next one. Bye.